Okay, so in this video, we're going to start talking more about solar power. In the last video, we talked about wind power, which was the first type of renewable energy source that we talked about. Um, when we talk about lots of different energy sources, ultimately the source of many different sources of energy actually come from the sun. Okay, so for example, the energy of the sun originally produced fossil fuels. Hydroelectric dams work with sun-lifted water because the sun, evaporates the water and then it rains into the dam, and so on. Um, Heat gradients caused from the sun create wind, which, as we talked about in the last video, wind is used to create electricity through the use of wind turbines. And so, in a sense, all these different energy sources tie indirectly back to the sun. So, with that being said, when we talk about solar power, we're not talking about any of those other energy sources, even though technically speaking, you could argue, solar power includes lots of different energy sources. When people talk about solar power, they're talking about energy derived directly from the sun's rays. And in IB physics, the two direct solar energy devices that you really need to know about are solar heating panels and photovoltaic cells. And for the most part, we're going to talk about photovoltaic cells because most of the time when people talk about solar power, that's really what they are referring to. They're talking about electricity produced through the sun's rays. Okay, so just to kind of give you brief descriptions of these two things. Solar heating panels are used to directly use the heat from the sun to heat, typically to heat water, but they can also be used to heat houses and whatnot. And you can read a full description in your IB physics textbook. Photovoltaic cells, on the other hand, photo means light and voltaic means, like voltage. And so a photovoltaic cell basically converts light energy, that is electromagnetic radiation from the sun, directly into electrical energy. And so, again, when most people think of solar power, they're thinking of electricity produced through solar power, which comes from photovoltaic cells. How that works is kind of difficult to explain, and so we're not really going to talk about that because that's beyond the scope of the course. Just a random fact, though. Um, Current solar cells have an efficiency between 10 and 20%, and so kind of keep that in the back of your mind as we're doing calculations. This chart kind of shows you the difference between photovoltaic cells and solar heating panels. This thing called a solar concentrator is another way we use solar energy. I've never seen that come up in the IB physics curriculum, but it is something that exists. You can find pictures of that online. Basically, my understanding is that it kind of um, uses like mirrors to focus light from the sun, or to focus the heat from the sun to boil water to produce electricity through like a thermal power station. Okay, as opposed to photovoltaic cells, which there is no thermal power station, there's no steam or turbines or anything like that. A photovoltaic cell takes in sunlight and directly produces electricity. Okay, and so this is actually, when we talk about photovoltaic cells and solar power, that this is actually the first example of electricity that can be produced without electromagnetic induction. This process has nothing to do with electromagnetic induction. All right. So just to kind of recap the concept of intensity, because intensity is key to doing calculations with solar power. Just to kind of recap the ideas of intensity, when you talk about intensity from a source, you're basically talking about the power per unit area incident on one location. And so we've actually talked about the situation in the past unit, in a way. But the sun radiates energy at a rate of 3.9 times 10 to the 26 watts. And the question says, what is the rate at which energy? When you see rate of energy is power. Okay, so it's still talking about power. What is the rate at which energy from the sun reaches Earth if our orbital radius is 1.5 times 10 to the 11 meters? And so the principle, which we've talked about this before, but the principle is that the sun puts off energy in all different directions. Um, and all the sun that all of the energy that the sun emits has to travel like spherically away from it. Okay, so if you imagine like a giant sphere centered on the sun, like a giant bubble, all of the energy that the sun puts out has to travel through the surface area of the bubble. And so because of conservation of energy, the energy going through the surface of the bubble at any given time is always the same, no matter the size of the bubble. But what happens is the bigger the bubble is, and this is a hypothetical bubble. The bigger the bubble is, the more spread out, or the lower the intensity is of that energy. Okay, and so if we want to find the intensity where the Earth is, let's say the Earth is over here, then basically we need to make the bubble, ignore my bad drawing, we need to make it so that the bubble has a radius of 1.5 times 10 to the 11 meters. And then what happens is that 3.9 times 10 to the 26 watts is spread out over a sphere with a radius of 1.5 times 10 to the 11 meters. Now, just to remind you, the area of a sphere is 4 pi r squared. And so we would divide this by 4 pi 1.5 times 10 to the 11 squared. And this type of calculation we'll see a lot in the next unit as well, when we talk more about like the what's called the solar constant. All right, so I'm just going to do this calculation. 3.9 times 10 to the 26 divided by 4 pi 1.5 times 10 to the 11 squared, and I get 1379.3 watts per square meter. Okay, meaning that at the location where the Earth is, this many watts is incident on the Earth for every square meter that gets hit. Okay, and so when you talk about solar power, you're talking about the size of solar cells. You have to take into account this is the intensity that hits the Earth's location per square meter. And so obviously the bigger area that's getting hit, the more solar power we can produce. All right, but this type of derivation, this is again what's called the solar constant in the next unit. That's something you'll have to be familiar with for the next unit as well. Okay, so pause there if you need to look at that some more. Okay, and so again, what this would mean is, let's say you're standing out where the Earth is, just like in space, and you have a solar panel that's 1 meter by 1 meter. Okay, and you're holding it up. Okay, that basically means that the power you could get from that solar cell, assuming it's 100% efficient, which it's not, would be, about 1380 watts. Okay, for a 1 meter by 1 meter cell, which is not a ton of power. All right, that's just the solution. So take a look at this example here. It says the intensity of the sun's radiation arriving at the Earth is approximately 1400 watts per square meter. We saw it's actually more like 1379 in the last example. If the peak demand for the entire US is about 800 gigawatts, keeping in mind 1 gigawatt is 1 billion watts, what is the land area required if we could capture this energy at 100% efficiency? Which remember, we can't, because most solar cells have, most like photovoltaic cells have an efficiency of about 20%. Okay, so ignoring that for now, let's do the math on this. All right, so we know I equals P over A, and we know that the intensity from the sun is about 1400 watts per square meter, and we need a power equal to about 800 times 10 to the 9 watts, right? 800 gigawatts. That's enough to supply electricity to the entire United States, not including the rest of the world, of course. So you can see here, just using basic math, we can just rearrange this equation. 800 times 10 to the 9 divided by 1400 gives us a very big number. In fact, it's so big I kind of want to do it in scientific notation. Let's see, 5.71 times 10 to the power. Let me count these zeros. 1, 2, 3, 4, 5, 6, 7, 8. 8 square meters. Okay, so that is approximately equal to, let's say, 571 square kilometers. And just to give you an idea of how big that is, if you take the city of Chicago is about 600 square kilometers. The entire city of Dallas is probably around 900 square kilometers. So this is a pretty big chunk of space. I think Carrollton is maybe like 40 square kilometers. So this is quite a lot of space that would need to be taken up. Not to mention, of course, that this is assuming 100% efficiency. Um, and really, we would have to multiply the surface area by a factor of about 5 if we're assuming 20% efficiency. Okay, so just to give you an idea about solar power. All right, so let's move on. Okay, so we talked about the efficiency of photovoltaic cells. This is just a short video clip talking about how much power it would take, or how much it would take to power the United States with solar energy. Okay, so you can check that out. And let's see, we've already talked about some of these things. This example is just asking, why is the solar intensity different for different parts of the Earth? Because what happens is that 1380 watts per square meter, as it hits the top of the Earth, it gets spread out over a wider area. And so if it gets spread out more, then that means the overall power received is reduced, and so that's why it's colder up north as opposed to like the around the equator where it gets more direct sunlight. All right, so you don't need to know how a photovoltaic cell works. Let us do a simple example with solar calculation though. So this says a photovoltaic cell has an area of 1 square centimeter and efficiency of 10.5%. If the cell is placed in a position where the sun's intensity is 1250 watts per square meter, what is the power output from the cell? All right, so first of all, we know I equals P over A, and we know the intensity is 1250 watts per square meter. So we can find out the power that's actually hitting the cell. Now, that doesn't take into account efficiency yet. As long as we divide by the area of the cell, which is 1 square centimeter. Now, you have to be really careful with the units, though, because centimeter squared and meter squared are not the same thing. So we have to do a unit conversion. And just to remind you how that works, when you do a square unit conversion, you have to put the conversion factor. So there's 100 centimeters in 1 meter, and then you have to square both sides. And so 1 square centimeter, you're not dividing by 100, you're actually dividing by 10,000. Okay, so that would be about 1 times 10 to the negative 4 square meters. All right, so as long as you don't make that mistake, this is a pretty easy calculation to do. So P here would be 1250 divided by 1 times 10 to the negative. Let's try that again. 1 times 10 to the negative 4. 0.125 watts. And that's just the power that's actually hitting the cell, right? Only 10.5% of that actually is output. And so P out would be 0.125 times 0.105, which takes into account the 10.5% efficiency. Okay, and so I get a power output of 0.013 watts, which is not a lot at all, as you can see. All right, so pause there if you need to look at that some more. So when you're doing these calculations, they're not anything complicated or anything like that. Just make sure you understand how to do square unit conversions. You understand how the intensity I equals P over A equation works. You understand how to do efficiency calculations, stuff like that. Okay, and then this example just kind of goes on to show, how much current is output. If you had 10 of these cells in series, what would the voltage and the current be? I don't know that you necessarily need to worry about that for this unit. This question, though, how many cells would you need to operate a 100-watt circuit? You would need, over 7,000 of these cells to operate a really relatively small powered circuit. Like 100 watts is not a lot. That's like, a light bulb or something. So, on the other hand, if you don't need a lot of power, if you ever see these calculators that have these photovoltaic cells on them, a calculator doesn't take a lot of power to use, and so you can power a calculator with just, 4 of those cells, as you can see. All right, so let's take a look at one more example really quickly. Actually, we can do this one in class, I think, because I want to talk about direct heating. All right, so let's talk about heating panels. All right, so I said this at the beginning of the video, but most people, when they talk about solar power, they're thinking of photovoltaic cells, but you can also use solar heating panels. And basically, a solar heating panel converts sunlight directly into heat, and that's used to either, heat a building like a home, or heat water so the home can have hot water. And basically, the way it works is you kind of layer some things in between, like a layer of glass, and on the bottom side you have a black absorber to absorb more of the heat, and you kind of pump water through this system. As the water goes in, it absorbs the heat from the sunlight, and when the water comes back out, you get hot water. When I say hot water, I mean, hotter than the cold water than you put in. Okay, and so that's kind of the idea. And this is just like another picture showing how that works. And so this would be effective to use, in really cold climates, like maybe the Arctic or Alaska, or places that are really cold but might still get direct sunlight. All right, so just to kind of show you a calculation problem with that, let's take a look at this. At one particular location, the average power received from the sun during a 6-hour period each day is 840 watts per square meter. The solar heater has an overall efficiency of 35%. It is required that during the 6-hour period, the solar heater raises the temperature of 140 kilograms of water by 25 Kelvin. The specific heat capacity of water is 4.2 kilojoules per kilogram per Kelvin. Calculate the minimum effective area of the solar heater. So there's a lot of stuff going on. You probably noticed that it's talking about specific heat capacity. All right, so let's start with that. I see specific heat capacity. I think right away Q equals MC delta T. There's only one equation in all of the IB physics that has to do with specific heat capacity. So I'm going to start there. That's my first instinct. All right, so I know the mass of the water. I know the specific heat capacity of the water is 4.2 kilojoules. That's 4,200 joules per kilogram Kelvin. And I know that the temperature has to be increased by 25 Kelvin. So delta T would be 25. Okay, and so keep in mind that the calculation I'm doing applies over a 6-hour period. Right, so this takes 147,000,000 joules of energy to heat this water up this much. All right, but the energy is spread out over 6 hours. And so I know power is energy over time. And so I can find out how much power is required to actually do that just by dividing by the time, the number of seconds in 6 hours. Okay, so 6 hours, each hour has 3,600 seconds. Okay, and so that's going to take 680.6 watts of power. So the water has to absorb energy at a rate, on average, of course, of 680.6 joules per second in order for the temperature to be raised this much. All right. Now, the question also tells me the average power received, or sorry, not the power, the intensity received by the sun is 840 watts per square meter, and that the efficiency is 35%. All right, so this is basically got to be my output power. I need this to be my P out because I need this many joules per second to heat my water. So what P in do I need? Well, I know, efficiency is pout over pin, and so my pin would be 680.6 divided by my efficiency of 35%. Okay, and so that gives me a pin of 1944.4 watts. In other words, I need enough sunlight to actually hit my solar cell to deliver this type of power. And now I'm almost done with the problem. The problem is asking me for the minimum effective area of the solar heater. Okay, so it's asking me for area. Obviously, it's talking about I equals P over A, and I'm looking for A. I know what I is, it's 840, and I know the P that's required to actually hit the thing is 1944.4. I do want to tell you, this is not what I would consider an easy problem per se. Maybe I make it look easy. Um, but you can see that there's actually like a lot going on in this problem, right? I get 2.31 square meters. Okay, and obviously, if I got more than that, then it would be more effective at heating the water by the 25 Kelvin. Okay, so if this was like a test problem, there's a lot of stuff going on here, right? There's a MC delta T calculation. There's a, taking that Q and finding what P out has to be. Then there's finding what P in has to be. Then there's using the intensity equation to find the area. And so a lot of stuff in topic 8, as you can see, just from looking at this one example, starts putting together all of the other concepts that we've learned over the past 2 years. Each piece by itself is not necessarily difficult, right? Um, there's no like crazy hard calculations, but you have to think through step by step what it is you're doing. All right, so pause there if you need to look at that some more. All right, so we will do, and this is just kind of showing the other steps. So we will do some more examples in class with calculations, but hopefully from everything we've talked about, you have a sense for how to do solar energy calculations. The last thing I want to talk about is what are some disadvantages of like solar energy? Because the advantages are self-evident to most people. Some of the disadvantages are storage, right? You can't really store the energy produced by photovoltaic cells. Um, Producing photovoltaic cells, or even solar heating panels for that matter, is very expensive, and it takes certain types of materials that are not necessarily cheap or easy to get. Um, and a big issue, of course, is timing, right? Because if it's nighttime, then you're not producing energy because there is no sunlight. Um, and so all of these are things, disadvantages to consider as far as solar energy goes. All right, so we're going to go ahead and stop there and maybe do some more calculation examples in class, but that is the gist of what you need to know about solar energy. So, as always, please let me know if you have any questions, and I'll see you guys in the next video.